Here in this video, we are solving a question that is given in NEET 2024 in electromagnetic induction. Let us see what is that question is first of all. The question says, a strong bar magnet is moving towards the solenoid 2 from solenoid 1 this way. You can see in the diagram clearly, this is solenoid 1, this is solenoid 2, this is a strong bar magnet is moving this way from A to B, this way. Right. The direction of the induced current in the solenoid is. So the first thing that we need to remember back is there is a law called Lenz's law. An induced EMF is developed in a coil in such a way that induced EMF always oppose the change in magnetic flux that causes that induced EMF, that causes it. So you have to understand it little carefully. According to Lenz's law, whenever there is a changing magnetic field, there is an induced EMF. But that induced EMF don't like to be induced itself. It want to be in a stable state inertia. And that induced EMF, that's why oppose the change in the magnetic flux that is causing it. See, for example, this is the south pole approaching this coil. So there is a current developed in this coil. Around the current there is a magnetic field developed. That magnetic field develops an induced current. The induced current develops in such a way that opposes the change in the magnetic flux that is causing it. So the induced current that is coming here, which generates induced magnetic field, behaves as if like it don't want that induced magnetic field, oppose the induced magnetic field. So as the south pole is trying to approach it, because of the induced current there will be another formation of a south pole in such a way that because of this south pole experiences a repulsive force. That means inside this coil a magnetic field is developed in such a way that here is a south pole and here is a north pole. And that's most important thing that you need to understand little carefully. So if you try to know what's the direction of that induced current to generate this magnetic field of north and south, then we can use the right hand thumb rule. You shall hold the thumb in the direction of magnetic field, that is along north pole. Magnetic field means north pole gives the direction of magnetic field traditionally. Then you shall be, to hold the thumb like that, you shall be curling your fingers. So I want you to see how do you curl your fingers. I just want you to hold this magnet with your hand and see how your fingers are coming, right? They are coming from the bottom of that to the top this way. This way it will come. They'll go back. Again they will go this way, right? They'll go back, come this way. So in which direction the current is moving is from here to here. That is from D to C. Hope you got it. You just hold your thumb this way. This is your thumb, and curl your fingers. I'm a very bad artist in drawing the fingers. I don't know how to draw it, but you are curling your fingers in such a way that from this bottom, these fingers will be coming up. So the current is in this way. So from D to C, there, right? So D to C is in this option. So this option is also quite possible. But look at the other case. There is another point, right? Look at this case. Here also the same. Here is the north pole trying to move away. The induced EMF is develops induced magnetic field in such a way that opposes it. To oppose the north pole, here is the formation of another south pole. This south pole attracts this north pole towards it, therefore it opposes it. So here is the formation of north pole and south pole like that. For that again you have to hold your fingers. Similarly, you shall hold your fingers this way and you shall curl your fingers, right? You shall curl your fingers in this way. Then earlier they comes in reverse to that of this case. So it happens from here to here. because the poles are reverse. Here is north-south, here is south-north. Then the current also reverse to this. So here is from A to B. So hence this is the correct answer. This is how we solve the problem. Thank you for watching.